Hello students, in this lecture we will be discussing about root locus. Now root locus is a second stage of stability. In the previous lecture we dealt with route criteria. There were certain drawbacks of route criteria. Now those drawbacks will be somewhat eliminated using root locus. So root locus is something different from your route criteria. But basically root locus is also used for checking the stability of a system. Now for this, let's consider a simple control system. Let's say this is K, let's say this is G1 C, and let's say this is H. Let's consider this negative feedback control system. Now we know that the characteristic equation for this system will be nothing but 1 plus the G open loop transfer function equal to 0. Now what is G open loop transfer function for this? It's nothing but the product of all the blocks, transfer function of all the blocks. So K G1 H, that is this thing. So therefore the characteristic equation becomes 1 plus K G1 H equal to 0. Clear? Now in this equation there is one parameter which is variable, and that parameter is our gain. So this is your variable parameter. Now in this, if K takes different values, if K is variable, obviously the roots of our characteristic equation will be different. So that means if we vary K from 0 to positive infinity, if we varies K from 0 to positive infinity, then for each value of K will have different sets of location of roots of characteristic equation. I again repeat, for each separate value of K we will get separate set of locations of characteristic equation. Now if all those locations are joined, the resultant locus will be our root locus. We'll explain this thing, how we vary K and how do we get different locations, and what is root locus. So basically just remember this, that root locus is nothing but it's a graphical method where K varies from 0 to infinity, and we'll study the stability of a system after getting the value of K. Clear? Now in this, there are certain rules which we should be familiar with before we start plotting a root locus for any given system. There are certain set of rules which are to be followed. Rules for root locus, they are very important, those rules, because those rules are to be followed one by one, and then only we'll be able to plot our root locus. So in the very first step, what we're going to do is, first we're going to write the characteristic equation for the control system. For this, remember this, that the root locus is always plotted for open loop system. It's always plotted for open loop system. Now suppose in this figure, what's the open loop transfer function? The open loop transfer function is K G1 H. Clear? So root locus is always plotted for open loop system. Now suppose our open loop system somewhat comes out to be something like this, like G is equal to K times numerator by denominator. I've written it wrong. Numerator by denominator. K numerator by denominator. Numerator means there will be some transfer functions in the numerator term and there will be some transfer function values in the denominator, because if we substitute the value transfer functions for K G1 H, so that is for this open loop transfer function, it is K G1 H. So obviously there will be some terms of transfer function in the numerator and some terms in the denominator. So let's say our open loop transfer function is this thing, which is in the standard form written as K numerator by denominator. Now let's say in the numerator term we have terms like S minus Z1, S minus Z2, S minus Z3, and so on till s minus zm. Clear? And in the denominator we have some terms like s minus p1, s minus p2, s minus p3 till, let's say, s minus pn. Clear? Now what are z1, z2, z3 and what are p1, p2, p3? I'll let you know just in a minute. Just remember that these are some terms appearing in the numerator and these are certain terms which are appearing in the denominator of our open loop transfer function, that is this sum. Now rule number 1 is root locus is always plotted for n greater than or equal to m. That means in the denominator term the number of these roots should be greater than the roots appearing in the numerator. That is, root locus is always plotted for n greater than or equal to m. That means in the denominator the roots should be of greater in number in comparison to the roots appearing in the denominator term. Clear? Now what are these n and m? N is basically your number of poles and m is basically number of zeros. Now over here if you see in the denominator I have written p1, p2, p3. p1, p2, p3 are called poles. z1, z2, z3, that means the terms appearing in the denominator, they are termed as zeros. So root locus says number of poles should be greater than or equal to number of zeros. Root locus is always plotted for this case. Clear? Now what are poles and zeros? Now there is a simple clear definition. Poles are those values of s which make our open loop transfer function, that is g, what? Equal to infinity. Clear? Poles are those values of s that makes our transfer function g equal to infinity. That means if I put s equal to p1, so p minus p1 will be 0. That means in the denominator we have 0. So anything divided by 0 is infinity. So those poles are those values of s that makes our system infinity. Now poles are represented by cross sign. So poles are represented by cross sign. Similarly, what are zeros? Zeros are those values of s that makes our transfer function equal to 0. That means z1, z2, z3. Obviously, if I put any random value, that s minus let's say s equal to z2. So if I put s equal to z2 over here in this part, it becomes numerator 0. So numerator is 0. That means our overall open loop transfer function is 0. So zeros are those values of s that makes the open loop transfer function equal to 0. Now zeros are represented by this dot sign. Zeros are represented by dot sign. Clear? So now just remember that in the denominator the terms appearing for s are poles. In the numerator the terms appearing in the numerator are for s are zeros. Poles are marked with a cross sign, zeros are marked for dot sign. So rule number 1 says poles should be greater than or equal to zeros. Clear? Second rule says that number of loci or branches, I'll explain what are loci and branches in a minute. Number of loci or branches are equal to number of open loop poles, that is equal to n. So if there are, let's say if there are 3 poles, like one s minus p1, s minus p2, s minus p3. Now open loop, obviously we are dealing with the open loop transfer function. So if there are 3 open loop poles, so number of loci will be equal to 3. I'll explain what are loci and branches in a minute. So just remember that this is rule number 2. Rule number 3 says root loci or root locus begin at pole and it terminates at zeros. That means root locus or root loci starts at pole, it will always start at pole and it will be terminated at 0. Now let me explain with this thing. Now suppose this is the complex system and somewhere here we have one pole and there is one 0 on this real axis. Clear? And on this, so that means loci, that is root locus will emerge from this pole and it will eliminate at this 0. It will eliminate at this 0. It will move towards this 0. Now this, what is this arrow? This arrow is your loci. This arrow is your loci. Now if, so in this case, number of poles is 1. This is pole. Number of pole is 1. So how many loci will be there? There will be 1 loci, and that loci will be shown by this arrow. Now this arrow starts from pole, it will eliminate at this 0. Now suppose if we have two poles, so that means one loci, so there are two poles mean two loci, so there should be two loci on this thing. Now rule number 3 says loci starts from pole. Okay, so one loci will start from this pole, one loci will start from this pole. What will happen? Now they both will approach towards each other. They will meet at a single point. That single point will determine later on. They will meet at a single point and then they will leave the real axis. That means they have a head-on collision with each other at a certain point on this real axis, and it will leave the real axis, and it will leave this real axis. Clear? That's your rule number 3. Rule number 3 says root loci begins at pole and terminates at 0. Fourth rule is, this is very important rule. Fourth rule says root locus segment lie on the real axis. First of all, it will always lie on the real axis, and it always lie on the left hand side of the odd number of poles and zeros. Odd number of poles and zeros, that means collectively the number should be odd. Now what is this root locus segment? Now if you see in this figure over here, whether in this figure or in this figure, you know, I've marked something, highlighted a real axis over here, this thing and this thing. So what is this? This is basically the root locus segment. Root locus segment is that part on the real axis where the root locus is plotted. You cannot plot root locus randomly at any place on this complex plane. It has to be plotted on the root locus segment. So root locus segment is very important. Root locus segment always lie on the real axis, number 1. You will always have it on the real axis. Second, where does you find it? It will always lie on the left hand side of the odd number of poles and zeros. I'll explain this thing. What is odd number of poles and zeros? Now suppose we have something like 1, 2, 3, 4, 5, somewhere 6, 7. Clear? Now suppose we have something, an open loop transfer function where we have 1, 2, 3, 4, 4 poles and 3 zeros. Clear? Now we have marked all of them over here. Now rule number 2 says that number of loci should be equal to number of poles. Now number of poles are 1, 2, 3, 4. So loci should be equal to 4. Right? We'll see how. Now for that, first, now loci always lie on the segment. That is also important. And first we need to find out the segment. Now segment lie on the real axis. So that means on this real axis, on this part, we'll have a segment. Now segment lie on the left hand side of the odd number of poles and zeros. Now what we do is, on this entire real axis, let's divide into certain sections. Let's say this is first section, second section, third section, fourth section, fifth, sixth and seventh. Clear? I again repeat. Now let's divide our entire this root locus into certain sections. Let's say this is my first section, this is my second section, from this point to this point. Now from this point to this point, third section, then we have the fourth section, fifth section, sixth section and the seventh section. Now we have divided our segment based upon this poles and zeros, these segments. Clear? Now on each segment, okay, I've deleted one pole. Okay, now we have one pole over here, right? I'll show it with this one. Right. Now let's take this section first, this part. On the left hand side of this segment, do we have any pole or zero? That means on this side, on the left hand side, on the left hand side, do we have any poles or zero? No. Okay, I just make a correction over here. It's not left hand side, basically it's your, sorry for the correction, this is right hand side, sorry. It's not left hand side, it's right hand side. It always lie on the left hand side. No, sorry, it remains same. Okay, my correction. It's always left hand side. It's always left hand side. Now for how to see this? Now on this segment, now clear, right? Now on this segment, on the left hand side, sorry, on the right hand side, let's see on the right hand side of this segment, do we have any pole or zero? No. So that means this is not the segment. Now this segment, on the right hand side, on the right hand side of this segment, do we have any pole or zero? Yes, we have this one. And what is this? This is 1. So 1 is odd. So that means this segment is your root locus segment. Now another segment, on the right hand side, on the right hand side we have one pole and one zero, which is even in number, because 1 and 1 is 2 even number. So this cannot be your segment. Let's take this segment. On the right hand side we have odd numbers 1, 2, 3. So this is the segment. This segment 1, 2, 3, 4. It cannot be this. Then this segment, yes, it will be, because on the right hand side we have 1, 2, 3, 4 and 5. Then this segment 1, 2, 3, 4, 5, 6. This cannot be. Then this segment, this goes up to infinity. So 1, 2, 3, 4, 5, 6 and 7. Yes, it's an odd number. Clear? So this is what the rule says. Lie on the left hand side of odd number. So the left hand, so this is the left hand side of the odd. This is again the left hand side of the odd, left hand side of the odd and left hand side of the odd. Clear? So this is what it is. Let me again repeat something. Let's again explain this thing. Now again let's plot another example. Suppose this is 1, this is 2 and somewhere here this is 3. Clear? Now again I repeat. Now let's divide into segments. That is first segment, from this point to this point. From this point to this point we have another segment. From this point to this point we have another segment. So we have 3 segments, and one we have the 4th segment from this point towards infinity. Now on each segment, now on this segment, is there any pole or zero on the right hand side? I don't think so. There is anything on the right hand side of this. So this is not the segment. Now second segment, on this segment, is there anything on the right hand side? Yes, we have one cross or one pole, so which is odd in number. So yes, this from this point to this point will have a segment. This segment we have even number, it cannot be this. Then on this segment till infinity, yes, because we have odd number 1, 2 and 3. So obviously the blue line represents the root locus segment. Clear? Now number of loci in this case is 2. So one will be shown over here because it starts from here and eliminate one. The other one will start from here and it will move towards your infinity. Clear? So rule number 4 is very, very important, because once we know the segment, then only we will able to plot the root locus. And further, root locus always lie on the segment. You cannot plot anywhere. It has to be on this segment only. Clear? Further, this was rule number 4. Rule number 5. Rule number 5 is number of asymptotes. Now what is asymptote? Asymptotes are basically the straight lines or the tangent lines to the curve. So asymptotes basically represents the it represents the the nature of the root locus, how the root locus looks like. So remember, this number of asymptotes is always equal to n minus m. That means suppose if there are 3 number of poles and there are nothing in the numerator, so 3 minus 0, so number of asymptotes will be 3 in number. If n is, let's say, 6 and m is 2, so the number of asymptotes will be 6 minus 2, 4. So always remember that number of asymptotes is always equal to n minus m. Clear? Now all these asymptotes, they meet at a single point, and that single point is known as center of gravity. Center of gravity, that is gamma, which is represented as gamma equal to sum of all poles, sum of all the poles. If there are 3 poles, obviously let's say one is at -1, the other one is -2, -3. So -1 plus -2 plus -3, that will be the sum of poles, minus sum of zeros divided by n minus m. So whatever that value comes out to be, that will be your center of gravity. That will be center of gravity. Clear? Center of gravity. Sometimes some other books they refer it as gravity can also be written as sigma a. It's nomenclature, nothing else, but the formula remains same. The center of gravity, sum of all the poles minus sum of all the zeros over n minus m. Clear? Also, all these asymptotes, they make an angle with each other as pi 2k plus 1 over n minus m, where k varies from 0, 1, 2 till n minus m minus 1. Clear? All these asymptotes, they originate from this center of gravity and they will make an angle with each other with this angle. That is 2k plus 1 over n minus m pi, where k varies from 0, 1, 2 till n minus m minus 1. Now suppose if n minus m is 3, so k will vary from 0, 1 and 2. So one will put k equal to 0, the second time will put k equal to 1, third time will put k equal to 2. So the angles will be what? Pi by 3. N minus m is 3, so pi by 3 of, so one will be pi by 3, the other one will be pi, the third one will be 5 pi by 3. Clear? So this is what it is about number of asymptotes. Next, the 6th rule is breakaway point. This is the most important point of the entire root locus, breakaway point. Now I'll explain what is breakaway point, but just remember that breakaway point always lie on the segment. Which segment? This blue, this segment, root locus segment. So it will always lie on this. Also, it represents that point where k, the parameter, is minimum. If you see, if you remember over here in the very starting, we said k is a variable. So obviously k variable, so it must have some minimum value and the maximum value. So k minimum value is always calculated from the breakaway point. So breakaway point is that point where k is minimum, and it always lie on the segment. Clear? Now how do we calculate breakaway point? Now breakaway point is calculated by this formula that says sum of all zeros, that is sum of this thing, that is I vary from 1 to m, should be equal to sum of all the poles, s minus poles, that is, let's say pj, because we used I over here, so j varies from 1 to n, that is this thing, that's the breakaway point. Also there is another way to calculate this breakaway point. We can use this method, it's a very easy method, or I've said that breakaway point is nothing where k is minimum, right? Now we know that our characteristic equation is 1 plus k times gs equal to 0. So what is k in this case? K is nothing but minus gs, 1 upon gs. K is 1 upon gs. So what will be k minimum? So dk by ds will give you your k minimum. So you can use this method, or you can use this method to determine your breakaway point. Clear? So these are certain rules which you should remember while plotting the root locus. Now let's take a simple example. With example the things will be much clearer. Now let's take a simple example. Now in this example the question is plot the root locus for the open loop transfer function, that is k upon s plus 1, s plus 2 and s plus 3. Now that's the open loop transfer function given. Now number 1, let's see. Number 1 is number of poles, that is m equal to 3. They are at minus 1, minus 2 and minus 3. Number 2, number of zeros, that is m is 0, because there is no such term of s in the numerator, so number of zeros is 0. So n is greater than m, so root locus is valid. Clear? Rule number 3, number of loci should be equal to number of poles, that is number of loci should be 3. Rule number 4, root locus segment. Now this is important, root locus segment we need to plot. Now let's see root locus segment. Let me take the fresh page. Now let's say this plot needed to be plot on a graph paper, so that will be easy. Clear? So you should use graph paper. Now let's say this is 0, minus 1, minus 2, minus 3, minus 4 and so on, and let's say this is 1, 2, 3, somewhere here 4, so minus 1, minus 2, minus 3, and let's say somewhere here it's minus 4. Now number of poles are at minus 1, minus 2, minus 3, and they are represented by a cross sign. They are to be represented by a cross sign. So let's plot it cross over here. So one cross is at minus 1, the other one is minus 2, and the other one is at minus 3. Now we have 3 crosses. Now segment, on the right hand side, on the right hand side of this, nothing. On the right hand side of this we have 1 odd in number, so this portion between minus 1 to minus 2 will have a segment. So we can, let's show it by a green line. Clear? This part odd even number, on this part, yes, from minus 3 to infinity we have the segment. So we can say root locus segment lie between minus 1 and minus 2 and from minus 3 to minus infinity. Clear? Now number of loci 3. Let's see. one loci will be here because it emerges from pole. So one pole is there, it leaves. One pole is there, it leaves from this side, and the other one leaves from this. Now the question you must be asking is, sir, why they have shown on this green portion, why not somewhere else? Because loci always lie on the segment. So if this part is the segment, loci has to lie on the segment. You cannot plot randomly at anywhere. Loci has to be plotted on the segment. So 3 loci, so we have 3 arrows. Now next part, fifth part, number of asymptotes. Number of asymptotes will be equal to n minus m, that will be 3. So what will be the center of gravity of this? Center of gravity will be sum of all the poles, minus 1, minus 2, minus 3, there is no zeros, by 3. So minus 1, minus 2, minus 3, minus 6, minus 6 by 3 is minus 2. So yes, that means this is my center of gravity. I can show it as sigma A. Clear? You can simply write it on the graph paper that sigma is also your center of gravity. For the time being, I'm just removing it because for the plot. Now we know this thing. Angles. Angles. Pi over n minus m into 2k plus 1. So n minus m is 3. So pi by 3 of 2k plus 1, where k varies from 0, 1 and 2. So the angles will be pi by 3, pi and 5 pi by 3. So how to plot the angles? Now we have a center of gravity over here. Put a d over here. We're going to put your d, angle d over here, and pi by 3. So first pi by 3, that means this is your 60 degree. Second pi, we put a d over here, and this is your angle pi. Third is 5 pi by 3, we put a d over here, and somewhere here is your angle. So these dotted lines are asymptotes. They are emerging from the center of gravity, making an angle of pi, 5 pi by, and pi by 3. That is, this is pi, this angle will be pi, this angle will be pi by 3, and this angle will be 5 pi by 3. Clear? So these are your angles. So right, so these arrows, these dotted lines, they represent the asymptotes. Now let me remove this part because we need a space over here to plot the things. Now next part is, once we are done with the asymptotes, the next part is we need to now draw the breakaway point, which is the important one. Breakaway point. Now breakaway point, I said, is nothing but 1 over s, sum of all the zeros, s minus z, equal to sum of all the s minus poles. Now there is no zero term, so this on the left hand side it is 0. Now poles, so that is s plus 1 over s plus 2 plus 1 over s plus 3 equal to 0. Calculate, solve this thing, we'll get the values of s. So it's a very simple, we're gonna get a quadratic equation, solve this part, and we're gonna get a quadratic equation. Your quadratic equation will come out to be something like 3s square plus 12s plus 11s equal to 0. Simple quadratic, so the two roots of the equation are s equal to minus 1.42 and s equal to minus 2.57. So you have two values of s. Now out of these two values, only one will be your breakaway point. So one value will be your breakaway point. Let's see which one. Now s equal to minus 1.42. Now where is minus 1.42 is lying? Minus 1.42 is somewhere here. And the other one is minus 2.57. That is somewhere here. Now out of these two, which one will be your breakaway point? Now out of these two, only this value lie on this segment. Lie on the segment, whereas this doesn't lie on the segment. So this value will be neglected. So hence s equal to minus 1.42 is the breakaway point. That is, this is the breakaway point. Further, I've also told you that two loci, they will meet at a single point. Now that single point is your breakaway point. So both these loci, they'll approach towards each other and they're gonna meet at this single point. So this we can say is our breakaway point. Clear? So we have calculated the breakaway point. Now we need to plot the root locus. Now for root locus, what we need to do is, now let's look at the shape of the asymptotes. Now we see the asymptotes are basically approaching towards the imaginary axis, right? So there are two asymptotes, out of three asymptotes, two asymptotes are approaching towards the imaginary axis. That means our root locus will also approach towards the imaginary axis. Our root locus will also approach towards the imaginary axis. So for that we need to go for the rule number 7, which I will not discuss. So rule number 7 now I'm going to discuss is the point at which the root locus cuts the imaginary axis. Now this rule is only valid when you see the asymptotes are moving towards your imaginary axis. Then this rule is valid, that is point at which root locus cuts the imaginary axis. For this rule, we're gonna prepare the Routh array. Now Routh array says we need a characteristic equation, that is this thing. So our characteristic equation will become s plus 1, s plus 2, s plus 3 plus k equal to 0. Clear? Now we're going to solve this thing. This becomes s cube plus 6s square plus 11s plus k plus 6 equal to 0. So now this is our characteristic equation. We'll prepare an array. Now their highest power is 3, so array should be 1, 2, 3 and 4. From this array we're going to find the value of k. So now let's say this is 1, this is 11, this is 6, this is k plus 6. This will be 66 minus k plus 6 by 6, and this is k plus 6. Now look at these values. For root locus, for the system to be stable, all these should be positive, right? This is positive, this is positive. Obviously k is always a positive, so this is positive. We have a doubt over here, that is 66 minus this. Now for unstable this should be negative, for stable it should be positive. Let's equate it to 0. So equal to 0 means it is on the verge of either stable or unstable. So from here, when we equate this equal to 0, that is 66 minus k plus 6 by 6 equal to 0, will have a value of k which comes out to be 60. So that means when we put k equal to 60 in this equation, or in this equation, it makes the system on the verge of stability. That means it makes the system on the verge of stability. So if I take let's say 60.1, just 0.1, it makes the system unstable because this will become negative. If I take 59.9, this becomes positive. This third row will become positive. The system becomes stable. So at k equal to 60, it is on the verge. Now this is the maximum value of k which we can take for the system to be stable. Maximum value of k which we can take is 60. Clear? Now to this row, the previous one, let's prepare the auxiliary equation. Okay, now let's forget about the auxiliary. Now we have this equation, so we'll put this value of k in this, so it becomes s cube. So it becomes s cube plus 6s square plus 6s square plus 11s plus 66 equal to 0. Clear? We substitute this k value in this. So we have s cube plus 6s square plus 11s plus this. Now let's put s equal to eta a. So when we put s equal to eta a in this equation, so we'll have some real part and some imaginary part. Let's say on solving, when putting s equal to eta omega in this, so we have 66 minus 6a square and we have 11a minus a cube, eta equal to 0. So we have real part and imaginary part. Now on the imaginary part, on the imaginary axis, the real part will be 0. So we put real part equal, now this is the real part, we'll put real part equal to 0. So when we put real part equal to 0, what do we get? We get a is equal to 66 by 6, that is 11 under root. So it becomes 3.32. 3.32. So that means the root locus will cut the imaginary axis at 3.32. That means somewhere here. Somewhere here, 3.32, somewhere here. So we'll have one point over here and the other point is somewhere here. Clear? So this is how we calculate the point at which the root locus cuts the imaginary axis. First we'll find out the maximum value, then we'll substitute that maximum value in the characteristic equation, substitute s equal to iota omega or s equal to iota a, calculate the value of a. So a comes out to be 3.32. That means this is the point where the root locus cut. Now we have 3 points, 1, 2 and 3. Simply join these points to get your root locus. So we can join these points and we have our root locus. So this red line is the representation of your root locus. Clear? Now over here at this particular point, k was maximum. K is having a maximum value, that is 60. When I take k equal to 60, the root locus reaches the imaginary axis. Sorry, root locus reaches the imaginary axis and the system is on the verge of stability. Now at a break-even point, at breakaway points, at this particular point, I said k should be minimum. Now what is this break-even point? Minus 1.42. So when I substitute this s equal to minus 1.42 over here, I can calculate my value of k. Now in this value, so over here, if I put s equal to minus 1.42, calculate the value of k. K, let's say, comes out to be 0.286. So that means at this breakaway point, my k is, let's say, 0.286. So this is the minimum value of k and this is the maximum value, and on this root locus we have infinite values between 0.06286 and 60. Clear? So this is what the root locus is. Root locus is a plot where k varies so that the system remains on the verge of stability. So anything on the left hand, or anything on this left hand side of the imaginary axis, the system is stable. So system remains stable if k is taken between 0.286 to 60. Once it reaches greater than 60, it reaches somewhere here on the right hand side, the system becomes unstable. Clear? So this is how we determine the stability using root locus. Now in the next lecture we'll continue with the root locus. We'll take some more problems and we'll discuss, suppose if we want to verify, suppose if some particular point is given. Now let's suppose if this point is given somewhere here, we are given some point, how do we test that this system, this point lie on the root locus or not? That we're going to discuss in the next lecture. Thank you. Now in case any query related to root locus, please feel free to contact. Thank you.